Alright, so this is version 3.0 of the Tycho software, which has just now recently been made available. So I would like to take just a short moment to go over the new features and improvements that you can expect to see in this version, and then wrap it up with a short demonstration. So to get started, the first thing you'll notice in this version is that it loads the image data twice as fast as before. So it's always nice whenever you can minimize the amount of time spent processing and loading data. The next item is pseudo-flat calibration. Not everyone has access to a flat frame for their images, or if they do, that flat frame is perhaps not adequate to achieve a sufficiently flat field. And so in this version of Tycho, it is able to compute a pseudo-flat for each image, which achieves not only a flat field but also a consistent background level from one image to the next. The centroid algorithm has also been revised. I used to use a center of mass function to compute the centroid of an object, but now in this version it uses a point spread function fitting approach. And so you'll notice that the centroids computed by this version of Tycho are now nearly identical to that computed by other astrometry software. And this ties in with the next item, which is that the measurements, the astrometry overall in this version have been much improved, as I have changed not just the centroid algorithm but also the plate solving routine. And so to actually evaluate this quantitatively, thanks to several users of this software who have provided data, I have in fact a catalog of 25 near-Earth objects. In other words, I have the raw data on those objects, and I use that as a sort of benchmark, again, to evaluate Tycho in comparison to other astrometry software. And so I will share those results in just a moment. But now the next item is the ability to perform alignment using the PixInsight software. So this should be welcome news to those who do not have Registrar, which up to now was the only alignment program that Tycho would interface with for performing an automated alignment routine. So this provides another option for those users. Finally, the last item here is the ability to attach ephemeris information to each image and the data set. So you can very quickly determine whether or not the object of interest is within the field of view of each image, as well as its speed and position angle for each image. So it's a convenient feature to have. So as I mentioned, pseudo-flat calibration, in an ideal world, you would have a consistent background level from one image to the next, but also within each image. For example, the pixels in the center would have equivalent amplitude to those in the corners. In other words, it would be a flat field. So you can achieve this now using a pseudo-flat, which essentially works by computing a sliding window around each pixel. The way that works is you take some number of pixels ahead and some number of pixels behind, or left and right if you're on the x-axis, and you compute a statistic value. So you can take the pixel value, divide it by that statistic value, and achieve a flat field, and also have a consistent background level from one frame to the next. So if you perform this process, then you do not need to perform normalization, as it has essentially in effect been performed during pseudo-flat calibration. So as you can see, the image on the left is a raw frame, and the image on the right is that same raw frame except with pseudo-flat calibration having been performed. So it achieves a very flat field, and I would say that if you do have a true flat that is optimal, then you can go ahead and continue to use that. Pseudo-flat is very comparable in performance usually, but the true flat is probably slightly better. But pseudo-flat is certainly better than none at all, and so in fact on these results here, I applied the pseudo-flat calibration routine to all 25 of the objects that I measured with Tycho. So what you're looking at here, the blue line represents reference software. So this is a very popular astrometry program used by many astronomers, and so I'm comparing that with Tycho. And so what I've done here is for each of the 25 near-Earth objects, I measured them in both programs, created 3 observations of each object, and then I selected the maximum, the measurement having the maximum residual. So as you'll note, residual lower is better. So in this graph here, you can see that overall, on average, Tycho appears to be performing with improved measurements. And so this is very good to see. I've spent a lot of time and effort to achieve this result. And so these are 25 data points essentially to help at least confirm that Tycho is indeed capable of performing very good astrometry. So yeah, PixInsight, as I mentioned, can now be used for alignment. A couple of observations here is that it does seem to offer slightly better resampling than Registrar. On the other hand, if a meridian flip occurred during image acquisition, Registrar seems to do slightly better in that scenario. But they are both very good programs for alignment, so if you have one, no reason not to continue using it. Finally, as I mentioned, you can attach ephemeris information to each image, and so it's very helpful to determine which image to discard from the dataset. If the object is not within the field of view, then that image is simply detracting from the result, especially if you're conducting a stack. It simply does not contribute any useful information. So it's another convenient feature to have. And so at this point, it is time for a brief demonstration. Okay, so this is 2019 QG, and these are images provided by station v3.0. As you can see, there are 36 of them. So we'll start off by performing calibration and then alignment and plate solving. So the calibration, I'm just going to perform the pseudo-flat technique, as I mentioned earlier. This is a process which works on each image, and it provides a consistent background level. In this case, you can specify what you want. I normally do 5,000 ADU counts. So anyhow, these are default values and they're mentioned in the user manual. Of course, you can tweak them however you want. So anyhow, I'll click OK on that. And for alignment, I'll use the PixInsight program for this demo. And then again, because we're performing the pseudo-flat calibration, normalization does not have to be performed because each image will result in having a consistent background level in that technique. So, okay, let's go ahead and get started. So we're performing calibration, and it's already now doing the alignment. So this is a script that is running in PixInsight. And now we're performing plate solving. Alright, and now the output is located here. So I'll go ahead and navigate to that directory with the images. And so again, this is 2019 QG, so we can go ahead and download observations of this object. It's no longer a NeoCP, it's a confirmed object by this point. So, and the purpose of this exercise is to kind of pretend like we are station v3.0. So up to this point, these observations would not have been available. So I will discard them from the set here. And when I click Attach Ephemeris to Dataset, this invokes FindOrb software, which in turn is able to compute the ephemeris for this dataset. This is a slightly modified version of FindOrb for this application, and so it will be made available for this release. So when I click Return Ephemeris, then you'll note that the columns in the image manager have now been populated. So column over here is pretty useful. It indicates whether or not the object is actually in the field of view. So if you have images where it is not, it's a good idea to remove them from the data set. Anyway, so we can proceed with identifying the object. There's a couple ways to do it. One of which is you could just simply open up the image viewer and say, okay, I want to stack the images according to the ephemeris. So you do that, and then you'll notice there's the object right there. So yeah, it's a couple of layers that you can use. These are hot pixels. We don't care about those. when I switch to this layer, it becomes more obvious that this is the object. So what I could do is simply double click that and then create a track, and then that permits me to create observations. So I can say verify track with 3 observations. Yes, that's obviously the object there. So when I do that, then we now have measurements of the object, and we can compare with existing observations. So we can first off determine, for example, what residuals we had originally. So 0.71, 0.69, well, 0.92 actually. And then the new observations here, of course, these are 3 stacks rather than 4, so it's not exactly apples to apples comparison, but it looks like 0.62. So these are good measurements. But anyway, the other way, of course, to do this is to run the tracker. So we can perform these steps. These are like usual, and the user manual will explain this, of course. Sensitivity threshold, I tend to use this value. It's fairly sensitive. Since it's a known object, that's fine. And then we can, in this case, we can use ephemeris from the data set, or we could type in our own limits for speed and position angle. So I click that, and most of the time this works fine. If the orbit of the object is sufficiently well known, then the upper and lower bounds here are usually acceptable. If the object has just recently been discovered, or it's not a very good orbit, then you probably need to adjust these parameters and widen the search space a bit. But we'll go ahead and click OK and see what happens. So it looks like it found it. This is track number 1. As you can see, the quality here is noticeably higher than the other tracks. So we can go ahead and verify it, and you can see it here in the image viewer. So if I do this layer here, it stands out a little bit. It's one of the trickier objects to distinguish from the background, I suppose. But in any case, that is the object. So I'll go ahead and designate it as such, and compare with existing. So we'll see how well these measurements. Again, 0.62 is what we had before on our max residual, and here we have a 0.49. So, and I've noticed this trend too. Generally, the synthetic tracker performs better than the manual track, if you will. So you'll generally get better measurements if you run the synthetic tracker. But sometimes it won't find the object, but usually it does. Anyway, so this is an example, and I will be putting out more tutorial videos on and some tips and tricks on how to do the trickier objects. But anyway, for now, this is a demonstration of kind of the new features. So I mentioned the pseudo-flat technique. Here you can fine-tune the parameters if you wanted to. It's already been, pseudo-flat has already been applied, so you didn't really need it here. But if I were to take one of the raw images, then you can see here's the raw image here, and if I apply the smoothing kernel, then you'll note what that looks like. So so anyway, that's 3 passes in this order statistic, meaning we're taking the lowest 1/3. So if we wanted the median, for example, then it would look like that. That's a bit more aggressive. And obviously, if we use the average, then this is the behavior that results. So the stars get blown up. So you would never really use average. You would use this order statistic instead. So more passes makes it smoother. So if I have just 1 pass, for example, then you'll note you get more of the object information like that. And the window length makes it more or less aggressive as well. So if I choose, for example, 3, then you'd almost just be subtracting or dividing by the image itself. And as I do 10, 20, then you can see the effect right there. So I generally do like 41 and 3 passes to smooth it out some. So that's a pseudo flat, and I've done that on all 25 of the near Earth object datasets that I have, and it has worked very well. And anyway, I guess that's about it for this demo. So thanks for watching, and see you next time.